Data scientists in the US get on average around $140,000 per year. And they're able to get such high salaries because they know three things which most people think are very difficult to learn. These three things are Python, SQL, and machine learning algorithms. And even between these three things, machine learning algorithms are what scares most people off. Everyone believes you need to be some kind of math genius. You need to know calculus, linear algebra, and all the heavy math stuff to be able to learn these machine learning algorithms. Well, here's the truth. In the next 2 hours, I'm going to teach you the top 7 machine learning algorithms that actually matter in real jobs and for clearing interviews, and you are going to realize they are way simpler than anyone ever told you. How do I know this? Well, I have been developing machine learning algorithms for some of the biggest tech giants like Meta, Cisco, and Wells Fargo. I have developed machine learning pipelines which are used by billions of people across the world. And not only that, I have conducted hundreds of candidate interviews. I have been part of dozens of hiring committees, and based on that, I know precisely what kind of machine learning algorithms knowledge you need to succeed in your job as well as to perform well in the machine learning interviews. And based on that, I have handpicked these 7 machine learning algorithms which I'll be covering in this course. We'll start with linear regression, which is the backbone and the very basic machine learning algorithm which everyone should learn. Then we'll go to logistic regression, which is a sister algorithm to linear regression, and it is also the foundational machine learning algorithm you need to know when at a later stage you want to learn deep learning. Next, I'll teach you decision tree algorithms, which is one of the foundational, very popular machine learning algorithm. And then I'll touch on how do you measure the model performance, especially for classifiers, because it is not as straightforward as it is for regression algorithms. Then I'll touch on k-mean clustering and some advanced decision tree based algorithms. And I'm going to teach all of these in a very intuitive and a very easy to understand way without using any kind of math, so that you can develop the intuition behind them. And intuition is all you need to successfully use these machine learning algorithms in industry as well as to crack most of the interviews. And I really hope that after going through these 7 machine learning algorithms, you'll have enough knowledge to use them successfully in any real world setting, as well as you should be able to answer a lot of interview questions related to machine learning algorithms. The knowledge of these algorithms will give you a high level overview of how machine learning algorithms work and what are the foundations behind them. And then you can use this knowledge to learn as many different other machine learning algorithms as you want. We have a lot to go over in the next 2 hours. So let's begin by going through linear regression, which is considered the most foundational machine learning algorithm. Hello everyone, in this video I'll try to give a very intuitive and easy to understand explanation of linear regression. I'll try to do it with the minimal amount of math possible. Easily explain the concepts of linear regression. I'll try to take a real life scenario of an ice cream man and for what kind of problem linear regression could be a solution to his problem. So let's take a hypothetical ice cream man. Let's say his name is Jeff. And Jeff has a small ice cream truck, and every morning he goes to an ice cream store to buy some ice cream. And Jeff has a problem. The problem is that if he buys less ice cream than he's able to sell on that day, then he suffers a loss. And even if he buys more ice cream than he's able to sell in that day, because he's not able to keep it overnight, ice cream goes bad and again he suffers a loss. So he needs to figure out what is the right amount of ice cream he should be buying for each particular day from the ice cream store, so that he doesn't buy too much and doesn't buy too less. So that is a question this Jeff ice cream man have to find a solution to. So now, since this ice cream man has been selling ice cream for a while, he sort of understands a pattern that there is a very strong relationship between how hot temperature is on that day and how much ice cream he's able to buy. He sort of used this information to make a vague decision of how much ice cream he buys on each particular day. Whenever the forecast shows that it is going to be very hot, he buys more ice cream. On the days when the forecast shows that it is not going to be very hot, if it is going to rain, then he buys less ice cream. So he knows for sure there is a relationship between temperature and ice cream sales. But he doesn't know what is the exact relationship so that he could arrive to an exact number on how much ice cream to buy, even he knows what is the forecasted temperature for the day. So curious with this thought, Jeff did an exercise. What he did was he tried to log the temperature for each day and how much ice cream he sold for that particular day. And he did it for a handful of days. And showing here this table, you can see that on days when the temperature is low, for example 19 or 22, we can see that he sells less ice cream, about 112 and 101. But on days when the temperature is high, for example 33, 35, he sells much more ice cream. So his hunch is right that there is actually a very strong correlation between the temperature and the ice cream sales, but he needs to find a way to quantify that relationship. So as a next step, what Jeff tried to do using this exact data, try to plot this on a two-dimensional graph. So let's say these are the axes which Jeff has plotted. Now let's look at each of these numbers one by one and then plot them on this chart. When the temperature is 19, it should somewhere show up here. Then the reading is 112, so probably somewhere around this point. Then for 26, it will be like here, and the temperature is 126, so somewhere between 100 and 50. So it should be somewhere here. Then just using this trend will fill out the rest of the points. Here we have plotted all the lines on the temperature and ice cream sales graph. And when Jeff did this exercise, he could clearly see that there is a very strong correlation between the two, and he can see that there is a line emerging here. So by looking at this, our hypothetical ice cream man Jeff, even when he does not have a lot of knowledge about math, could see that there is a trend line which could fit this pattern. Jeff can take a ruler, and let's say by looking at this, he came to a conclusion of drawing this line right here. We can see that this line sort of captures the trend given in these dots on the graph. The beauty of this trend line is that by using this line, he can now estimate how much ice cream he will sell a particular day for a given temperature. Let's say that for the next day, if the temperature forecast is 15, here look at 15, see where it intersects trend line, then seeing what is the corresponding value for the ice cream sales. So it will be somewhere around 90 ice cream sales. And similarly, if on a higher temperature days, let's say for here, he wants to know that what would be the estimated ice cream sales when the temperature goes to, let's say 40, he can just follow this trend line, go up here, and see that it will be somewhere around 270. This solves Jeff's problem. Now he has a very concrete way of finding what the estimated ice cream sales would be if he knows what is the maximum temperature for the next day. But when Jeff started looking at this graph, he started having some doubt about how good this trend line is, because it is entirely possible that the trend line should actually be somewhere like this, or maybe a little bit on this side. So how would we know that out of all these lines possible, what is the line of best fit? Now, as Jeff tries to solve for this problem on how can he find the line which best fit this data, he had another thought. Looking at this chart, you can think that he wants to create a line which minimizes the error. By error, I mean the distance between each of the dot on the plot, the estimated line. For example, you can say that this is slightly an error, this is slight bit, this one is on chart, and then this is another error. So Jeff can try to see that what is the error for each of these points, and then sum it up so that he could get the calculation of what is the error. Then he can try to create another line and then another line, then try to find the line which has the least amount of error. And then that would be the line of best fit. Now, in order to do this exercise, Jeff created these measures. These are the maximum temperatures and ice cream sales as we just saw before. Now he has created what is the trend line value for each of these maximum temperature, then calculated the difference between this and this. This is our error basically. Now he has a reading of 11, minus 21, 13. Minus sign comes depending on the dot is above or below the line. If it is below the line, then the difference is negative. If it is above the line, then the difference is positive. And then Jeff thought of just summing all of these up, calculate the total error. Here is a problem in this approach. If we look at this one, this is plus 11 and then the next entry is minus 11. If we just sum up them, both will cancel out each other. And at the end you would have a result which could actually be negative, which means there is no error at all. Or it could be close to zero. However, for individual points we see there is a lot of error. To overcome this issue, a very simple approach is that we just take the absolute value of each of those. Which means that wherever we see a negative sign, we just make it a positive. So this is already positive. Here it is negative, we also make it positive. This is negative, we again make it positive. This is already positive. So on, we make every one of these positive. Then we just sum all of them to come up with one number which tells us how much total error there is. In this case, we can see that the total error sums up to be about 95. As we know that for this line, the total error is 95. We can again try to create another line. Then using the same technique, try to get an error for that as well. Let's say for this one, the error is 95. Then we create a slightly line which is lower, and then we get, let's say, a total error of 106. Now we know that the error is increasing as we keep going in this direction. We have to go into the opposite direction. So now we move the straight line towards this, then again calculate the error. And let's say this time we see that the total error is 74. Now we know that the error is decreasing. So we'll keep going into that direction until we see something like this, that the total error is about 20. And then the next time we try, see that the total error again goes up back to, let's say, 40. So now using this technique, we could find that what is the right amount of error. So now by looking at this data, we could see that the optimum line should be somewhere between these two values. Now the good thing is that we do not actually have to take the ruler and draw the line and keep doing it again and again and again. There are much better ways to do it. And when we look at linear regression, there are actually two ways to solve the problem. First is that of iterative approach. In this case, we sort of take one measurement, then see what is the total error, then we keep going until we find a solution which is the most optimal. The other solution is that of using some mathematical formula. And this is also called the closed form solution. And the rationale behind this is that when we look at this straight line, there are basically two variables which we are trying to optimize for. We first write the equation for calculation of this error. Once we have the mathematical equation for this error, so ideally we want this error to be approaching zero. So we use some math to find the parameters which gives us this error as close to zero as possible. As I want to make this video very intuitive and easy to understand, I'm intentionally leaving out most of the mathematical details. Once you have developed these intuitions, feel free to go look at the other resources, find the math behind them. I hope once you have the intuition, understanding the math would become much more easy. Now, before I go further, I wanted to illustrate a little point here. That the approach we explained here, which is we just take the absolute value of all these differences, then sum them up. This is a very popular way of understanding if the line is the optimum line or not, and it is called mean absolute error and abbreviated as MAE. Because we are just taking the mean, which is a fancy way of saying average, of all these absolute values of the error. Another approach which is used more frequently, that of using mean square error, or MSE. The reason people favor this second approach more is that when you take a square of a number, even if it is a negative number, it gives us a positive number. So that we definitely need positives. That's why we are doing the absolute. Taking a square has another very positive thing, which is that for numbers which are large, the square becomes even more large. And in this way, since this is an error which we are trying to reduce, taking the approach of MSE penalizes the large errors more. So that is why researchers most of the time favor MSE more than they favor MAE. Now, if we look at all the steps we have followed so far, which is looking at the data, getting that trend line, calculating the error, and then finding the line of best fit, these are a lot of steps anyone to do manually. The good thing is now we have the power of computers to help us solve most of these problems. Now let's look at the example code of how can we use Python library scikit-learn to do it in just a handful of commands. For example, if this is the data you have, X is representing your independent variable, which is temperature in this case, and Y represents the thing you want to predict, which is the ice cream sales in this case. You can just pass it on into this single line, and it will train the model. It will do all the heavy lifting of finding out what is the line of best fit, calculating the MSE, MAE, everything. And once you have this model trained, you can use it to predict any new number you like. For example, in this case, you can pass in what would be the temperature for 35 and it will give you the result. And not only you can get the prediction for a single number, you can pass in a series of temperatures and it'll give you the prediction of all the estimated sales for all those days. You can also try to see that how well your model is trained. So if you run this command of finding what is the score of your model, it'll give you the R square of that model. Let's see what is R square. So the two approaches which we have explored before, which is MSE and MAE, they are both fine. They give us what is the total error for the line of best fit. But they have a problem. The problem is that, let's say if you train a model and it tells you that the MAE value is, let's say, 354. Now, how would you know that is this a good number or a bad number? Ideally, we want the score metric to be something like a percentage, so that when someone tells you the numbers are 70%, you know that the model is slightly good. If they tell you it is 100%, you know it's very good. When they say it's 0%, you know it's total trash. So for this purposes, the MSA and MAE are not very suitable metrics to report because the number in itself doesn't tell you if it is a good number or a bad number. To overcome this challenge, scientists came up with a very clever new way of calculating the error, which is called R square. So the way R square is calculated is to take the MSE, which is this guy, which is basically a mean of square error. The way R square is calculated is that you compare how good your prediction line is as compared to if you have just predicted the average value for the response variable. So let's go back to our original graph. So here we have this line, our prediction line, and let's say for comparison of it, we take another line, which is just a mean value of all these ice cream sale value. So let's say if the mean is somewhere here, and let's say if its value is about 150. So now we'll see how good is this line compared to this line, which is just a mean value. Because the reason we compare it against this is that this is a very easy to compute benchmark, which we can use to see that how good our estimations are as compared to if we had just predicted the average value. So we calculate both MSEs. We calculate MSE of prediction line, and then we calculate the MSE of average line. And then we basically take a ratio of these to calculate the R square. So the formula for R square becomes this. It is 1 minus MSE of mean of average value, MSE of average value divided by MSE of predicted line. Now this R square value could be one of the four scenarios. One is that we see R square is equal to 1. What does this tells us? That this number is 0, which means that the predicted line is so much better than the average value that this entire number almost becomes 0, and when we minus it from 1, it is almost 1. So this basically means that the line is perfect. The second scenario is that R square is 0. Now what does this mean? It means that this number comes up to be about 1, which means both above and below the denominator, they are equal value, which means both errors are almost the same, which means that the predictions are just as good as the mean value. The third scenario is the R square value is less than 1. This means that your predictions are even poorer than if you had just predicted the average value. The fourth scenario is that you have R square value which is between 0 and 1, and this is most likely scenario which you'll encounter for most of your models which you'll train. And if the number is closer to 1, it means the model is better. If it is closer to 0, it's not so good. So using this Python code, you can easily calculate the R square and it'll give you the R square value of your linear regression model. Some other useful things which you can get out of this linear regression model in Python is that it'll tell you the intercept value as well the coefficient for each of the variables which you use. Now let me explain what it is. When you look at the equation of a line, it is usually represented with y is equal to mx plus c. Now in the case of linear regression, a lot of time people use beta 1x plus beta 0. So c is basically substituted with b0 and m is represented with b1. So what these beta 1 and beta 0 actually mean is that this is intercept and this is the coefficient. And what do they mean? Let me actually draw the graph to explain to you what do they mean. Let's say again you have this graph, and then you see this line of best fit because you had some data points which were scattered somewhere around here. So what does intercept mean? So intercept is the point at which your straight line, it intersects x is equal to 0 value. So wherever it intersects, let's say if y is equal to 4 here, then your intercept becomes 4. So this is where straight line intersects the x is equal to 0 point. And what is coefficient? Coefficient is basically slope. It is basically the slope of this line. Now the reason these two numbers are sufficient for us to estimate any straight line is that all we need for a line is that what is the starting point. Say if we know this is the starting line, then we need to know what is the slope. If there is no slope, it will be just like this. If it is low slope, then it will be something like this. If it is high slope, it is something like this. So just based on that, we can draw the line. So we just need to know what is the starting point on x is equal to 0. Then what is the slope? Is it high slope, low slope? So we'll get a number mathematically for the slope. If we just know these two numbers, then we can plot any line. Another beauty of this is that once we have figured out what is the value of beta 1 and beta 0, for each value of x, which is temperature in this example, we can find what it would be the value of y. So for example, if we know that the value of beta 1 is 5.5, and then we know that beta 0 is, let's say, 25, where it intersects, where this line intersects x is equal to 0 point. And then for each value of x, let's say if we want to know what would be the estimated sales for when x, which is temperature, is 35, if x is 35, we can just plug all this value into this equation and it will give us the result. Linear regression is a very powerful tool. You can use it to estimate pretty much everything. You have the data of some of the factors which influence its outcome. But it also has a very serious limitation, which is that the input needs to have a linear relationship with the output. Going back to the example of ice cream sales, now let's say if we know that as the temperature increases, the ice cream sales also increase. But if it becomes very hot, then we see that there is actually a decline in the ice cream sales. Then the relationship will not be linear anymore. Let me quickly show it to you. So let's say this is a graph for ice cream sales. And this is temperature, this is sales. We can see a point like this, but after a while, after a certain temperature, let's say if it is 45 degrees centigrade, we can see that it again comes back, comes down. So now this relationship is not linear because you cannot create a single straight line to capture this trend. It has to be something like U to fit it. But the reason I wanted to point it out is that whenever you're trying to use linear regression for solving whatever you're trying to solve, always try to see the distribution of the data and the output first. Only use it for the cases where the relationship is linear. Now in this entire example, I've just used one input variable, which was temperature, and try to predict the ice cream sales. In most practical cases, you do not have to just stick with one variable. Actually, you can use as many variables as you want. Just make sure that the variables you are using are not very much correlated within each other. For example, do not use temperature in centigrade and temperature in Fahrenheit as two different input variables, because if there is a strong correlation between the input variables, that will create problem with the performance of the model. So what could be some useful variables where our hypothetical ice cream man can use to even further accurately predict the estimated number of ice cream sales? One could, of course, could be temperature, as we have seen. You can also look at if it is a school holiday or not. You can also look at it is like if it is expected to rain or not, because if it is raining, then a lot of people do not go out and hence there will be a drop in ice cream sales. That's all for today's video. In this video, I'm going to give you a super easy and a very intuitive explanation of logistic regression. Logistic regression is a very fundamental and foundational machine learning algorithm. It is the backbone of any other classification models and also a key concept to understand if you want to learn deep learning. Most tutorials out there for logistic regression, they are very math heavy and do not give a very intuitive explanation of the algorithm. So in this video, I'll try to take a real life example and I'll try to explain to you that how you can use logistic regression to solve problems like these, and I'll try to use the minimal amount of math to intuitively and clearly explain to you the concepts of logistic regression. And I'll also show you that how it is related and to some extent derived from linear regression, which I've covered in a previous video. If you haven't watched that video, do not worry, because I'll give a brief recap of linear regression in this video. If you have watched that video or already know what linear regression is, feel free to skip the next 1 minute, where I'll be giving a quick recap of linear regression just to make sure that we all are on the same page. For linear regression, we took an example of an ice cream man, and since he knew that there is a strong correlation between the maximum temperature of the day and the ice cream sales he saw, he wanted to quantify that relationship. So when we looked at this data for maximum temperature of the day and the ice cream sales, we saw that there is a strong correlation. For days when the temperature was low, for example 19 or 22, we saw that the ice cream sales were also lower. But on the days when the temperature was high, for example 33 and 35, we saw that the ice cream sales were also high. So we wanted to quantify that relationship so that for the new day he could easily calculate what the estimated number of sales would be. And for that, we plotted the ice cream sales versus the temperature, and we saw a trend emerging like this. So clearly there is a relationship between temperature and ice cream sales, and in order to make that relationship concrete, we drew a trend line through it using something like this. And this trend line was very powerful because for each new day, he could say that, for example, if see that the temperature is here, let's say 35 here, he could see that what would be the equivalent number of sales for that, and that will be his prediction. But the problem with this approach was that as we look at the data, there are more than one possible trend lines. So this is a trend line we draw, but we could have easily draw a trend line like this, or we could have easily draw a trend line like this. So there are multiple possible trend lines. So we wanted to know how can we find the line of best fit. And for that, we looked at the errors. An error is the difference between the line and the point. We saw that this is the difference. So this is error. And we saw this is the difference, this is the difference. So these are all differences, which is the gap between the prediction line and the data point. In an ideal world, there should be no gap. The line should be going through all the data points and there should be no gap between those, and that will be a zero error scenario. But in most cases, we see that there is a gap, so we wanted to quantify that gap. So we started looking at the gap between the actual data point and the prediction line, and then we try to sum it up. But there was one problem. The lines which were above the data point, they were showing positive error, and the lines which were below the data point, the error was showing up to be negative because we are taking this point and then subtracting the line. Now, in order to overcome that, we took the absolute values of the differences, and that gave us the value of mean absolute error. So this is the error we are calculating, and we are taking the absolute values of these, and then at the end we take the mean value, which is just an average. So this gives us a concrete way of calculating the error. Now, though this is a very valid way to estimate the error, there is even a slightly better way in which you basically take the square of the error instead of taking absolute value. So that is MSE, where S stands for square. And the reason this is better is because when you take a square of any number, it becomes positive even if it is negative in the beginning. And also the square of large numbers is even larger. So it penalizes the large errors even more. Then we saw that how we can use libraries like scikit-learn to very quickly and effortlessly calculate all these things within seconds with just a bunch of lines of code. And nowadays, when ChatGPT and Google Gemini is there, you can ask it to create the code for these predictions and it'll do the work for you. So you don't even have to write the code. And finally, we saw that though these mean absolute error and mean square error values are good, the problem with these is that let's say for any data point, I run this algorithm and I get the mean square error value of, let's say, 720. Now, I don't know if 720 is a good value or a bad value. So ideally, we wanted a score value which is very intuitive to understand by just looking at the value. The difference is the same as, for example, if I tell you that in some math exam, I got 800 marks. Now, you don't know if 800 marks are good or bad. But if I tell you that I've got 89% marks, now you can tell that these are good numbers. So in order to do the same thing here, scientists came up with a measure of R squared. And that is basically a comparison of how good your this prediction line is compared to if you had just calculated the average line across all these data points. So R square value tells you that compared to the average value of your data points, how good your prediction is. So this is a very quick recap of linear regression. If you still need help with that, go watch the previous video. And if you are still with me, let's look at the logistic regression now and see that how it builds on top of this knowledge to help us solve even other slightly different problems. To understand logistic regression, let's look at a different data. Let us say we are trying to estimate if someone has high blood pressure or not based on their body weight. And after taking some measurements, let's say we get a data like this. We can see that there is a trend for people who are low on weight, for example, 75 and 82 and 81, we can see that most of them do not have a blood pressure. But for people who are high on weight, for example, 138 kgs, they do have high blood pressure. So we know there is a trend line, we know there is a correlation, and high weight leads to high blood pressure. Now, trying to do the same exercise as we did for linear regression, let's try to plot these lines on a graph. But we have one problem. The problem is that to plot anything on a graph, we need to have numerical values, where here we have no's and yeses. Now, a very quick way to do it is that we treat anything which has a value of no equal to 0, and anything where we see it is yes, we take it as 1. By doing this, we can represent this data in a numerical form, and then we can do all the fancy math on top of it. So let's try to plot it on a graph. So this is our x-axis where we have the weight in the kgs. And for our y-axis, we just have two values, which is 0 representing no blood pressure, and then 1 which representing high blood pressure. And now let's plot all these data points on our graph. So now once we have drawn all these data points, which tries to either go through all the data points, which is clearly not possible here, so at least we can try to create a line which has the minimal amount of distance from the data points. So let's say by looking at this data, we got a trend line which looks like this. Now let's see if we can use this line to estimate if for a new person, given their body weight, we can tell if they have high blood pressure or not. So let's say a new person comes in with a very high weight. Let's say their weight is 140, and now we want to see if they have high blood pressure or not. So we can go up and see what's the value at this data point, which is, let's say, 1.8. Now, by looking at this number of 1.8, can we tell if this person has high blood pressure or not? We wanted to know if it is yes or no, if they have high blood pressure or not. But all we got out of this trend line is a value of 1.8. Now, how would we interpret it? Ideally, the output should be 0 or 1, so that we can tell if they have high blood pressure or not high blood pressure. So now one way to do it is that we clip the endings. So instead of going all this up, we just cancel this and we make the trend line like this. And we cancel all the negative values here and make the trend line like this. So now we have a new trend line which goes like this and this and this. Now let's see if we can use this trend line to give a prediction for a new person. Let's say a person comes up with a weight of about 100. Now what is the value of the trend line here? Let's say we go up and let's say this is 0.6. Now we wanted the values to be either 1 or 0, but we got a value of 0.6. How would we interpret it? Now, a very intuitive solution to this problem is that we, instead of taking the outcome as 1 or 0, we take the output as a probability or likelihood of someone belonging to that class. So in that case, we can see that 0.6 basically means 60% likelihood of someone having high BP. Now helps us solve a problem because we are getting probability distribution as an output rather than a binary yes or no. And this is even more useful than just getting a binary yes or no, because it gives us a likelihood of someone belonging to that class rather than just 1 and 0. And then we can adjust the threshold for cases where we want to be more sensitive to 0 outcomes or 1 outcomes. And the way we try to mathematically do this is by using a sigmoid function. It is a mathematical function which goes like this, where y is equal to 1 over 1. And the beauty of this function is that whatever value of x you pass it on into this, it stays between 0 and 1. The other benefit of using this sigmoid function is that it even makes this curve more smooth. So the sigmoid function output becomes something like this. It is even more smooth between the transition from 1 and 0. And another benefit of this, which you would later understand why it's a benefit, is that instead it asymptotes towards 1 and 0. What it means is that it stays very near to 1 as we go towards positive infinity, and it goes very near to 0 as we move towards negative infinity, but it never becomes fully 0 and it never becomes fully 1. Why it's a benefit, you'll see it shortly. So because of all these benefits, we use sigmoid function to estimate this trend line. Now, as we have come up with a solution on how we can use a trend line, which is not a straight line, but instead a sigmoid line, through this to find the approximation for a new data point. But it leads to another problem, which we also ran when we were doing linear regression, which is when you look at this data, there are actually many lines which are possible. For example, there is a new line which could go like this. There is also a new possible line which could go like this. So out of all these lines, which are green, blue, red, and could be many more, how would we know that which line best fits this data? And the way scientists solve that problem by using a function which is called maximum likelihood estimation. And this maximum likelihood estimation is a very important concept to understand because it does not just get used in logistic regression, but has a lot of other use cases. It is also a very important question which gets asked for the interviews for machine learning roles. And it is slightly difficult to understand. Most of the explanations which you see out there are just explaining the math of it. So you can definitely memorize all those equations, but I bet you that even if you ask experienced data scientists out there, 90% of them would not be able to clearly and intuitively explain to you what is maximum likelihood estimation. So in this video, I'll try to keep the math low and I'll try to give you a very intuitive and hopefully very easy to understand explanation of what is maximum likelihood estimation. Maximum likelihood estimation is actually very similar to the way we calculated mean absolute error or mean square error in the linear regression line. And the fundamental concept there is that we try to estimate that what is the error or distance between this trend line and this data points which we are observing. Now the problem with the logistic regression is that our trend line, which is this sigmoid line in this case, it represents likelihood of someone belonging to that class. So we have to change the way we think about errors instead of just absolute difference to what is the difference in likelihood. Now to easily understand maximum likelihood estimation, let me again draw the plot we were talking about. So on y-axis, if someone has high blood pressure or not, x-axis indicates their weight in kgs, and it started from 80 and went all the way to 140. And then on the y-axis, we just had two outcomes. One is 0, which is no high blood pressure, and then there is 1, which is they have high blood pressure. Now the data point distribution we saw was something like this. Most people who were on the lower side of the weight did not have blood pressure, and most people who had on the higher side of the weight did had high blood pressure. But then there were some people who had low weight but still had blood pressure, and some who had high weight but still did not have blood pressure. So there was a little bit of anomaly in the data. And then let's see if there are some people here. Cool. So in the previous step, based on this data, we draw a sigmoid function which went something like this, and realize that this asymptotes towards 1 here but does not really touches 1, and this asymptotes towards 0 but never really touches 0. Now let's see how we can calculate the maximum likelihood estimation for this line. So basically what maximum likelihood estimation says is that if we know that this line is true, then what is the likelihood of us seeing these data points? So if this line is true, then what is the likelihood of us seeing these data points? Now let me explain what does it mean. To do the actual calculation of maximum likelihood estimation, we have to look at each of these data points, and then we have to see if this trend line is actually true, then what is the likelihood we would see this data point. So in this case, we can see that if someone, let's say, have a weight of 140, if this probability distribution is correct, then what is the likelihood of us seeing this data point? So in this case, it is almost 100%. It is 99.999%, but we can say that it is actually 100%. Because if this is actually the trend line, then if someone has a weight of 140, this matches here, it means that the value of this line here is about 0.99, which means 99.99% probability or likelihoodness. Same goes for this line. It is again 99.99. For brevity's sake, I'll just say 100%. For this one, it is not 100%. It is slightly lower than that because the line has not reached almost 100. So let's say I'll say 80% for this one. For this one, it is even lower. So let's say 70%. And for this one, it'll be about 0% because if this is the actual trend line, then someone having a weight of 82, their probability of having high blood pressure should be very low, as we can see. So it will be about 0.001%. And then we do the same exercise for these points. What is the probability of someone having no blood pressure if this trend line is true? And as we can see, it is almost reaching 1. So their likelihood of not having a blood pressure would again be very, very low because it is almost reached 1 here. So it will be 0.001%. And then what is the likelihood of someone not having a blood pressure if they have a weight of somewhere here? Let's say if it is 95. We can see that intersects here. So the probability of not having blood pressure would be somewhere around, I'll say 40% based on this. What is the probability distribution of someone like this? It will be around 10%. And here it will be almost 100%. So for someone having this blood pressure, it will be about 90%. For someone like this, almost 100%. And again, almost 100%. Now, once we have the probabilities or likelihoodness estimated for each of the data point, if we know that this trend line is correct, then the next step is very easy. We just multiply all of them, and that gives us the maximum likelihood estimation. So let's say we multiply these, all of them, and we get a number which is, let's say, 0.04, which will be our maximum likelihood estimation. So this will tell us that how good or bad this trend line is. Ideally, this trend line should be closer to 1 because if we see everything is 99.9, 99.9 and almost 100%, then when we multiply all of them, it will again be 100%. So if the product of all of these is, let's say, 0.01, then to calculate MLE, we just have to take a log of it, log of this value, and then through maximum likelihood estimation, we try to maximize this value. So whenever we are comparing two such trend lines, we can calculate the maximum likelihood estimation for each of these lines, and then we can see what is the value. And whatever gives us the most value, that is the line of best fit. And that is what we finally use to make the rest of the predictions. Now, as you can see, it is a lot of work to do manually. Luckily, we do have help of computers to help us solve problems like these. So let me quickly show you that how you can use Python library scikit-learn to quickly train your own logistic regression estimator given these data points, and then how you can use them to make a prediction on any new data point. So this is how you initiate this model and then fit it on the training model. X here represents the independent variable, which for our example was the weight of the person, and then Y represents the dependent variable, which in our case was if they have high blood pressure or no. And it is represented in zeros and 1. 1 indicate they have high blood pressure and 0 indicate they do not have high blood pressure. And within a couple of milliseconds, the model would be trained. Now you can use this to make predictions on the new data points. Let's say if I want to know that if this new person with this body weight, they have the blood pressure or not, I can just use this command of classifier.predict and pass on the weight, and right there it tells me if they have high blood pressure or not. Another very useful feature is that you can not only get the value of 1 or 0, since the model has calculated this sigma line which we have represented here, you can actually use this to get the probability of someone belonging to the class of if they have high blood pressure or not. So the syntax slightly differs. Now you'll say classifier.predict_proba and then pass on the weight, and then it will tell you the probability of someone belonging to that class. And just like logistic regression, you can pass on as many weights as you want and it will tell you if all those people would have blood pressure or not. And by using the predict proba command, you can also see what would be the probability of someone having a blood pressure in all the data points you have passed it. And if you want to know how well your model is doing on some test data, you can just pass in the test X and test Y. It will give you the score of that model. Now the score which it gives is that of accuracy. Now accuracy is not always a very good measure to score a classifier. For example, let's say if you're trying to detect a fraud in a banking transaction and you have trained a classifier for that. Let's see, for every 1 million transactions, there is just one fraudulent transaction. Now let's say if you just train a very dummy classifier which predicts no fraud for every single transaction you pass in, that dummy classifier would be right 1 million times when there is actually no problem in the transaction. But the one transaction which has the fraud occurring, your model will even for that say that there is no fraud. Now when you calculate the accuracy of this model, it will be 0.999999%. Now, of course, on paper it looks good, but that model is useless because no matter what transaction you pass it on, it will always say that it is not a fraudulent transaction. So when we have this kind of imbalanced data set, then accuracy doesn't truly represent what we care about. Another word of caution I want to make here is that when you use the .predict command in this classifier, it by default takes 0.5 probability as a threshold. Anything below 0.5, let's say 0.3 or 0.4, it classifies at 0. Anything above 0.5, let's say 0.6 and 7, it classifies at 1. Now this works for a lot of use cases, but again, going back to the example of if you're trying to find the fraudulent activity on credit card transactions, and let's say based on this classifier, you're trying to build a system which notifies you if there is a probability of someone misusing the credit card. Now, if your system only alerts you when the probability is 0.5, then that is actually dangerous. You want your system to alert you even if the probability of fraud is 0.1% or even lower. Now, to fully explain these two questions, first, if accuracy is not the right measure, how else you can score and evaluate different classifiers? And second, if 0.5 is not always the right threshold, then what is the good way to calculate what should be the right threshold? In this video, I want to give you a super easy and very intuitive explanation of decision tree classifiers. Decision trees are one of the most popular machine learning algorithms out there. If I have to look back in my 10 plus years of machine learning experience, I can tell you without any doubt that the machine learning models I used most of the times were tree-based models, usually decision trees or their advanced versions like XGBoost, gradient boosting trees, etc. One of the reasons these models are so popular is that they are very flexible to use. One, they can use any kind of data without much pre-processing, which means that the input variables don't necessarily have to be fully independent, and they are very good at capturing even the non-linear patterns in your data, which means that you can pretty much pass on all the input variables which you think could be useful into the model, and the trees are very good at determining which factors are useful and which are not. Another superpower of these decision trees is that you can graphically look at the finally trained model output tree and then see that how the model is doing the reasoning just like a human does. Most of the tutorials on decision trees I've found are very technical and math heavy. In this video, I'll try my best to make it very light on math and very heavy on intuition so you can easily understand how a decision tree is built and how the models are trained on it. As I said, decision trees mimic the human decision-making logic, which is also sort of tree-based. For example, if I want to know what to wear and I have to make a decision on that, it will go like this. Am I going outside or am I going to stay at home? Then am I going to a formal function or I'm just going to a grocery shop so I can wear something casual? And even on top of that, there could be factors like what is the temperature out there, and based on that, what I should be wearing, or what time of the day it is. If it is a day event, I'll be wearing something different, and if it is a night event, I'll be wearing something different. So if you look closely, you'd realize that the human decision making is actually a decision tree based logic. And same is the way we tell computers what to do. If you look at any code, it is based on if conditions. If this, then do this. If this, then do this. It is basically a tree-based model of making a decision. Now, to explain this concept, let's look at the Titanic dataset. I'm assuming all of you are aware of the 1913's tragedy of Titanic, where a lot of people unfortunately lost their lives. The reason I'm using Titanic dataset here, that it is one of the most popular machine learning toy dataset out there. Though the actual dataset out there has many features, for the simplicity of my example, I'll just pick about dozen rows and just 3 columns to illustrate my point on how a decision tree model actually works. So for this example, I'll just be looking at factors of what is the gender of the person who was in the Titanic, what was the class of the cabin they were traveling in. Because one thing we observed from the data is that people who were in the elite cabin survived much more than the people who were in regular cabins. And the third thing we'll look at is that were they traveling with family, which means that they have some children or some dependents with them or not. And based on that, we'll try to see that if they survived or not. So now let's look at this data set, and then let's see that how an actual decision tree model works and make decision and get trained on this data. Now there are many versions of decision tree algorithms out there. The one I'm going to use in this example, it is the one which is the most popular. It is called ID3, and ID3 decision tree classifier is always a binary tree. That means that every stage it takes a feature and then it looks at what rows have class value of this versus the other, and then keep dividing. Let's see what it looks like for this Titanic dataset. So this is here just under a dozen example rows from the Titanic dataset. You can see that we have columns of gender, cabin type, if they're traveling with family or not, and then whether they survived or not. And then we have people who are either female or male. Their cabin type is either regular or it is elite. And some of them are traveling with family or not. And then at the end, we see that how many of those actually survived and how many did not. So when we talk about binary decision trees, at every stage, we take a feature. So for example, it is feature 1, and then we divide it based on values 1 and then value 2. And then we take feature 2, and then at every stage we pick another feature and then another picture, and then we keep dividing. That is why when you look at the Python or any other code implementation of these decision trees, you will see that the code is very highly recursive in nature, because if you, for example, if this is a tree and you look at it in a standalone way, you can see that this is a separate tree under this bigger tree. Okay, so enough of theory. Let me explain how a decision tree will be built on this data set, and I hope that along the way you will build the intuition for it. So the very first thing which we have to figure out is that what should be this root node from which the entire tree starts building. Now at every stage we want to create a root node which has the most prediction power to predict this output class. Now, to understand which of these features among gender, cabin type, and family has the most prediction power, let's look at this. So we can see that when we look at gender, we can see that 3 of them survived. For males, 3 of them survived, 2 did not. Female, 2 survived, 3 did not. And when we look at cabin type, we see this distribution: 1 survived, 4 did not for regular. And for elite, 3 survived, 1 did not. So we can clearly see that cabin type has more prediction power than gender, which sort of seems mixed. And then when we look at family, we can see that again, people who were traveling with family, they survived in 1 case and did not survive in 3 cases. And who were not traveling with family survived in 4 cases and did not survive in 2 cases. Now we want to know which of these features between gender, cabin type, and family had the most power in terms of separating this class of survived or not survived. And the way we mathematically calculate it is called entropy. And entropy is basically a measure of impurity of the classes for each of the variable. For example, when we separate based on gender, we see that the output is very much impure. It is 3-2 and 2-3 among survived and unsurvived. When we look at cabin type and divide it between regular and elite, we can see that the output is slightly less impure. So the purity level is high. And then when we look at the family type, we can see that it is also slightly better and less impure. So when entropy is basically impurity and we want to decrease it. Now there is a mathematical formula to calculate entropy, but I want to explain to you what the intuition behind this is. The value of the entropy, it varies between 0 and 1. 0 basically means only one class is present, which means the impurity in the data is 0. When it is 1, it means half and half, which means that the impurity in the data is maximum. And usually for other cases, it is between 0 and 1. And what we do is that every time we split the branch, now among all these candidate variables, we'll pick the variable which has the least amount of entropy. Now there are some online calculators which you can use to calculate the entropy, but when I calculate the entropy for this case, the winning candidate was cabin type. But because even as you can intuitively see that when we split the data based on the cabin type, we can see that we get a very clear class separation. We can see that people who are in regular are more likely not to survive than people who are in elite cabins, which are much more likely to survive. So because of this, the root feature for our decision tree will be cabin type. And then as it is a binary tree, it can take two values. One value is if the cabin type is regular, and the other is that if it is elite. Now in these nodes, we'll be looking at a subset of the data. At this stage, on the left side, we'll just be looking at the data where the cabin type is regular, and on the right side, we'll just be looking at the data where the cabin type is elite. So this is what the data looks like on the left side, and this is what the data looks like on the right side. You can see that for this data here, the cabin value is regular for all the rows, and for on here, the cabin type value is elite for all the rows here. Now again, we come to another decision, that what feature should we use to again split the data here and here. Now since we have already used cabin type, so this is out of the question. We have to either use gender or we have to use with family. We'll again do the same calculation of calculating the entropy for gender and then for family here, as well as on the right side, and determine that which one has the least amount of entropy, and then we'll use that to make the further split. So let's look at the data here when the cabin type is regular. We can see that when we divide the data based on gender between male and female, male survived almost on equal basis. So we can see that the value here, when it is half and half, it is 0.5. And if it is totally separate class, that is only one class exists, in the case of female, we know that the value is 0. Again here, the value is 0 of entropy. This is not half and half, so it should be 1. So it should be somewhere between 0 and 1. Let's say it is 0.5. Now, when we sum up both of these, we can see that for gender, the entropy is 1, and for with family feature, the entropy is 0.5. So with family is the winner here. So here we'll use the feature with family. Now let's look at the data on the right side. All of them had elite cabin. That is what this branch is. Cabin type we have already used, so let me exclude this. Now we have to see which has the low amount of entropy between gender and with family. And when I look at the distribution of it, if I divide the data based on gender between male and female, I can see that this thing has an entropy, let's say 0.5. This thing has maximum entropy of 1. This is half and half, so it is 1. And this is full class separation, so entropy here would be 0. Now when we sum it up, we can say for gender it is 1.5. And with family it is 1.0. Now if we pick a feature which has the minimum amount of entropy, we should be again picking with family here. Now again, the answer here is with family, but it's not necessary. It could have been different. And since I have picked with family here, just for this example's case, let me pick gender here to see that what the decision tree would look like. Okay. So now we have the data here. As we know, for with family feature, there are two potential outputs. If they are yes, they are traveling with family, and no, they are not traveling with family. And same is the case with gender, if they are male or if they are female. So now at each of these, we again have to make a decision based on which feature we have to use. So now when we look at this data, wherever the class separation is maximum. For example, when the person is female, we can see that they survived in pretty much every class. So we do not have to further divide this tree because pretty much everyone in this class survived. So here we will not divide this tree anymore. We can say that this is the final node, which is also called leaf node. And everyone here will be predicted as survived. And same story is true on the left side as well. We can see that when we split on the with family feature, anyone who was traveling with family pretty much did not survive. So here again, we can say that this node does not have to be divided again, and everyone in this did not unfortunately survive. But since these had some impurity, we are going to again split these two. So let's see what the data looks like for these two cases. So here the data looked like this, here the data looked like this, and here the data looked like this. So here, since we have already used cabin type and family features, the only feature which we can split on is that of gender, because that is the only feature left. And here, since we have used gender and since we have used cabin type, the only feature left is if they are traveling with family or not. And the possible values here is, let's say, male, female, and here it is yes or no. So in this case, as we can see, when they are traveling with family, which is this value is yes, they never survived. So our final answer would be not survive. And in the case when they are not traveling with family, which is these two cases, they survived in both cases. So our final output would be. And in this case, we can see if it is female, there's just one data, they did not survive. And in this case, even if they're male, there's just one data which they did not survive. Using all this, we can see that we have built an entire tree which we can use to make a prediction about any future person if we want to know if they are going to survive or not. For example, if we want to know someone who is in elite cabin is female and not with family, if they're going to survive or not, we will first look at this, we'll come here on this branch, then we'll say since it is female, they'll go to this branch, and then we can say that they are going to survive. I hope this explanation was easy to understand and easy to follow. Now a question might arise in your mind that here we were looking at only variables which had two potential output, which is either it is an elite cabin or a regular cabin, or it is female or it is male. What about if there are cases when there are more than 3 possible classes? The answer to that is very simple. Again, since we have to make a binary decision tree, which could just have 2 branches, even if there are 3 possible classes like A, B, and C, we'll pick any one of these classes, for example A, as the right branch, and the remaining of the classes, for example B, C, as the left branch. For example, if this is the feature and it has 3 possible values, A, B, and C, we have to make 2 branches. So let's say this would be A and then this would be B and C. Now the other question is, what if the input feature is a continuous variable? For example, the age of the person who is traveling in the Titanic. Because in that case, we take every possible value as sort of a splitting point and then see which one offers us a least amount of entropy. So the total number of calculations to calculate the best feature are much more. For example, let's take 2 scenarios. One, we just have 2 features and both have classes A and B, and this one has, let's say, C and D. So A and B are 2 possible classes for feature 1 and C and D are 2 possible classes for feature 2. So first we'll see what is the entropy of A and then entropy of B, and which one has the least amount, we'll just pick that, and we'll do the same exercise for C and D and we are done. Let's say if there is another scenario where we have 2 features and feature 1, just like here, has 2 values, possible values A and B. We'll look at entropy of A and then entropy of B, and then we'll pick the minimum. And let's say if feature 2 is a continuous variable, and let's say its values are between 1 and 100, then we have to calculate the entropy for 1, then entropy if we want to split the data on 2, and then for 3, and so on till 100. Now, since computationally this is very ineffective, so the way we do it is that we order the data based on this variable. For example, if the values we see are 7, 13, 29, and 41, then between each of these, we'll take what is the middle number between these, and we pick one as a threshold. And then what is the middle number between these two, and then we pick that as a threshold. And then what is the middle number between these two, and then we pick the threshold. And we just calculate the entropy for these middle numbers and see which one gives us the least amount of value. Now, as you can tell, that the calculation for this could become very complex, especially once you have hundreds of features and millions of data points. The good thing is that we do now have help of computers which can help us train a decision tree classifier with just a bunch of commands. Let me show you how easy it looks like when you're using a machine learning library like scikit-learn to not only train a decision tree classifier, but also make predictions based on that. So with this single command of decision tree classifier, you can initialize a decision tree classifier, and then you can pass on the input variables as well as the output variable to train it with this just one single command. Once the model is trained, you can make the prediction based on any future dataset with just using this predict command, and you can even evaluate the performance of the model by passing on these test variables and the test output variable. Now, one thing I want to highlight is that though decision tree classifiers are very powerful, one thing they are prone of is that of overfitting. Going back to the example of the decision tree which we created for our Titanic dataset, we can see that as the decision trees become longer and longer, they train very well to the training dataset, which sometimes mean that they lose the general patterns which are hidden in the data. Now, there are a bunch of ways in which you can try to minimize this overfitting. One is that you train it with a vast amount of data so that they are trained on so much data that their chances of overfitting on the data are minimal. Most of the libraries have a parameter where you can define that what should be the height of this tree. So don't let this tree become too long, otherwise your tree would be overfitting to the data it has seen, which is the trained data. So a good practice is that you restrict the height or the maximum depth of this tree so that it generalizes on the data much more. Now, the other option which you can use to minimize the chances of overfitting is that if you let it train by default, it will grow, the tree will just keep growing until it has all the leaves with just one class. And that in a lot of cases mean, for example, here with just one row. So in the decision tree classifier libraries, you'll see there is a feature which asks for what are the minimum number of samples needed to make the further split. Now, if it is 1, the model in this case will come and create these branches. But if it is 3, since it needs to have at least 3 samples to go beyond, it will restrict here and these further branches will not be created. And the final, probably the most recommended option, that you use some ensemble trees. Random tree classifiers, XGBoost, and gradient boosting trees are all examples of such ensemble trees. I'll be covering this in another video of this series. In this video, I'll give an intuitive and very easy to understand explanation of how do you measure the performance of different machine learning classifiers, especially when you are dealing with imbalanced dataset. So we'll touch on a lot of technical concepts like accuracy, precision, recall, confusion metrics, F1 score, calculating area under the curve of ROC, and much more. And I'll try to simplify all these fancy looking concepts in the simplest possible terms. So let's say that you have trained a machine learning classifier. You take a bunch of independent variables to calculate a binary output, 0 or 1. Since in this video I want to emphasize on how you deal with imbalanced data, you're trying to predict fraud in the banking transactions. So the output of your model would be if it is fraud or not. And the input variables could be what is the amount of the transaction, when it's happening, what is the distance from the last transaction, etc., etc. So there could be multiple independent variables which you can use. And while training the model, you have seen that there are about 1 million zeros, which is non-fraud transactions, and then you see 1 fraudulent transaction. So in nutshell, the ratio between non-fraudulent transactions and fraudulent transaction is million to 1. Now the problem with just measuring accuracy is that even if your model for your entire test set predicts that it is a non-fraudulent transaction, it will still be 1,000,000 times right and only one time wrong. So your model's accuracy would still be 0.999999%, which is almost 100%. So now on paper, though you'll get an accuracy of 100%, but your model is actually garbage. It is totally trash, totally useless, because it will never alert you for any fraudulent transaction, and for every incoming transaction, it will just say that it is a non-fraudulent transaction. So if you have set up some alerts based on if you see high probability of fraud in any transaction, it should alert you. That system will never alert you because it will never see high probability, because your classifier is always saying it is a non-fraudulent transaction. So what can we do about this kind of scenario? Well, the first step is that we create a confusion metric. So though the name is confusion metrics, but it is a very simple concept, and you can draw it in just a couple of seconds. So what you have to do is you have to draw a 2x2 table like this, where in top you have predicted yes and predicted no, and then on the left you have actual yes and actual no. By yes, I actually mean that the value would be 1 and no would be 0, and the same here. And then you look at the model's performance on a test data set, and then you fill out these boxes in this table. So in this box, you'll fill out what is the case where the actual value is 1 and the model also predicted 1. How many cases the actual value was 1, but the model said no or 0. For how many cases the actual value was 0, but the model predicted 1, and for how many cases the actual value was 0 and the model also predicted 0. So as you can see, these would be the correct answers where the actual value was 1 and the model also predicted 1, or the actual value was 0 and the model also predicted 0. And these would be the wrong cases where the actual value was 0 but the model predicted yes, or where the actual value was 1 and the model predicted 0. So you want to maximize values in this quadrant and minimize the values in this diagonal. And just by creating and looking at this confusion metric, it will give you a very good idea of how good or bad your model is doing, especially for minority classes for which you do not have a lot of examples in your training as well as test data set. But then the question is that how do you report to someone how good or bad your model is doing? And also, if you have to make an adjustment on the probability threshold based on which, if you decide it is a 1 or 0, then how you can tweak it. So because of these two issues, we calculate two other values, which is precision and recall. Now the way they are calculated is that precision is basically true positives divided by true positives plus false positives. Now what is a true positive? A true positive is basically this value right here. Positive here basically means that what if the model said it is a class 1 or 0. And this basically tells if it is a true prediction or false. So we can see that the model predicted positive and it is a true prediction. The model predicted positive here, but this is false prediction. The model predicted negative here, so it is negative, but it is false because the actual value was 1. And the model predicted negative here, but it is true because the actual value is also 0. So this is how we calculate precision. Similarly, the formula for recall is true positive divided by true positives and false negatives. Now, if you try to memorize this formula and try to see that how it maps to this table, and then try to do the math in your head that what does precision and recall actually mean, you will never be able to understand it. So let me give you a very intuitive, easier explanation for both of these. So once you understand that, then you never again have to run into a confusion of what is precision and what is recall. So let's look at recall first. Now, what does word recall mean? It is basically related to memory, and it means that if you have seen something or if you have memorized something, how well are you able to recall that? So recall in this case is also that. It basically means that of all actual ones, how many did you correctly classify it with? So it is basically asking of all the ones in the data, how many were you able to correctly recall? So this is where the word recall comes in, and this is what it intuitively means. So let's say if your actual data had 10 ones, then of all those 10 ones, how many your model was also able to say that these were ones. And once you understand this intuitive explanation of this, you can also step back and then try to derive the formula for this, which is we can see that the denominator here is all the actual ones. So it is basically TP, and let me draw the confusion metric again so that you can see what I'm saying. So we want to see what are all the actual ones. So we can see this is this part here. So this is all the ones, and then we want to say how many did you correctly classified as one, and this is this part here. So it becomes, this is the formula. Now precision word, it comes from precise, right? Which means that whatever you're telling, how correct or good that information is. So basically the intuitive definition of precision is that all the ones which you have predicted, how many of them were actually ones? Of all the examples where you have predicted as one, how many were actually ones? And by understanding this intuitive explanation of it, you can again go back to your confusion metric and drive the formula for this. That we can say that for all where prediction is one, and this is where the prediction is one. So we can see that the denominator would be TP plus FP, and the numerator would be what subsection of this was actually true. It is this part. So it will be this. Now this precision and recall, they are very important concepts whenever you're trying to use a classification machine learning algorithm, and especially when you're dealing with imbalanced data set, which for practical cases is almost always true. I've been into this profession for 15 years, and I don't really remember a time that when I looked at the data and I found the distribution of zeros and one almost identical. It is always skewed either towards 0 or 1. So whenever you train a machine learning algorithm to classify that, it is super important that you understand what is the precision of your model, you understand what is the recall of your model. It is also a very important interview question. So understand the intuition behind precision and recall instead of just memorizing the formulas, which would do you no good. So I hope the explanation here is useful. Recall is based on memory. It is basically saying that all the ones out there, how many were you able to correctly classify? And precision is related to how precise your outputs are, which means that of all the ones which you have predicted, how many actually were right or precise answers. And once you understand the intuition, you can definitely write the formulas as well. Now precision and recall are slightly opposite of each other. So in a model, when you're trying to make the precision number high, you would see that the recall would be dropping. And same is true for recall. If you try to make the recall high, you'll see that the precision numbers would be dropping. So then the question is that which should you prioritize, recall or should you prioritize precision? Let me give a very loose guidance for that. If there are scenarios where you don't want to miss out on any positive event, for example, credit card fraud detection, then you should try to prioritize recall. So in other words, if the cost of inaction is high, then you should go for precision. And similarly, if the cost of action is high, for example, if you're trying to train a model, in which case the tax department should do a detailed audit of someone. Or let's say if you're working in a marketing department of a company and you want to send out direct mail where the cost of each mail is $5 or something. So you only want to send it to people where you have high probability that they will buy from you. So since the cost of action is expensive, so in that case, you should try to prioritize precision. Now, there would be some scenarios in which you do not have a very clear preference or clear understanding of if the cost of action or inaction is very high. In that case, the general industry practice is that we sort of take an average of these and then try to see what gives us the best result. And this average is called F1 score. Let me explain what it means. To better understand F1 score, let's look at this chart. So let's say you have this chart, and on the x-axis you have different thresholds based on which you make a decision of if the class is 1 or 0. So the lowest value is 0.0 and the highest value is 1.1, and this is in the middle, and this is the threshold. And on the y-axis you have value between 0 and 1, and this basically tells you that how your model's precision and recall is doing as you change the threshold for decision. So let's look at recall first. What you would see is that your recall would be 100% when the threshold is 0, and your recall would be near 0 when the threshold is 1. It will basically have a curve like this. So this is precision. So now when you look at recall, it will have an opposite trend. It will go like this, let's say. So as you can see that when the precision is high, the recall is low, and when the recall is high, the precision is low. So then the question is that what threshold should you take? Now, if you have a clear understanding if the cost of action or inaction is very high, then you can definitely, based on some business use case, make the decision. But if that's not a clear priority, then you basically have to find a balance between both. Now, one very intuitive and easy option is that you just take the average of these two, and wherever that average is high, you just take that value. Now you can take the normal mean, but scientists have discovered that if you take the harmonic mean, it has an added benefit that it penalizes the extreme values more. So that's why when we take the mean value or the average, it is not the normal mean. Instead, we take the harmonic mean. And that harmonic mean is called F1 score. And if you plot it on this, it will go something like this. And then it drops down. So once we have plotted these charts, then we can see that at what point is the value of this F1 score maximum, which we can see is this point for this particular data, which could be, let's say, 0.4, and then we take this as our threshold for deciding if the class belongs to 0 or 1 class. Now there is another evaluation method which works even better than F1 score. It has a very funny looking name, so let's look at the name first. This is called Receiver Operating Characteristic, or ROC curves. To explain why it has such funky looking name, let me explain the origin of this. In the World War II, fighter jets were relatively a new invention, and to minimize the damage from enemy's fighter jets, radars were invented. Now, countries wanted to know how well their radars are performing in terms of identifying and alerting if they see an enemy fighter jet. And to measure the performance of these radars, this receiving operating characteristic curves were introduced. So receiver here basically means radar, and operating characteristic basically means its performance. So receiving operating characteristic or ROC curves were introduced to measure the performance of radars. But since then, they have been used to measure the performance of any other system, which gives a binary output of if an event is happening or if it is not happening. And as you can guess from the origin story, two inputs which radar gets: one, that there is no enemy fighter jet present, and second, there is an enemy jet present, is very imbalanced. 99.999% of the time, there won't be any fighter jet present, and only it's 0.001% of the time that the enemy jet will be presented. So these ROC curves are specifically designed to help ascertain the performance of systems where the class is very imbalanced. And the best thing about these is that they give you one number which you can use to measure and evaluate the performance of your model and compare it against other models. And also, based on this, you can help decide what should be the right threshold you should use to define if an outcome should be 1 or 0. So now let's see how these ROC curves are created. On the x-axis, you have false positive rates, or in other words, where the prediction is 1 and actual is 0, and on the y-axis you have true positive rate, where the prediction is 1 and also the actual value is also 1. And now, one by one, you take different thresholds, starting all the way from 0, and then by looking at 0.1, 0.2, till you reach the final threshold, which is 1.0. And based on each of these thresholds, you will see that some dots will be plotted on this line. Now, in the case that the model performance is totally random, the false positive rate and the true positive rate would be almost equal for pretty much all the thresholds you test. So from 0 all the way to 1.0, as you use different thresholds for predictions, you'll see the data point will be distributed at equal distance from both of these lines. So it'll be a straight line, something going like this. And this would be the case when the model prediction is as good as random predictions. Now, just like when we were evaluating linear regression, we used the mean value of the output variable as the benchmark against which we compared the model's performance. Just like that, in this case, we use this diagonal line to use as the benchmark against which we will evaluate the model performance. Now, in an ideal world, when the model performance is very good, you should see a curve which goes like this. It touches the upper left corner. But in most practical cases, the curve would be somewhere in between. So it will be going something like this. Now from this curve you can tell that this model's performance is better than this diagonal line, but to come up with a number which can tell you how better it is, we calculate the area under the curve. So a simple explanation for this is that if this is the total area and if this diagonal line is dividing it into half, then we know that the area under the curve for this diagonal line would be 0.5, because this diagonal line is dividing in half this entire surface area. And when we measure the area under this curve, it would be all the area which is here, represented by these horizontal lines. So now as we know that the area under this diagonal line is 0.5, we can calculate with the help of math that what is the area under the prediction line. And let's say in this case it is 0.7. Now by looking at these two numbers, 0.5 and 0.7, we can tell that the model is relatively better as compared to this prediction baseline, which is just as good as a flip of coin. And the best part is that this number which we get, it is very insensitive to the imbalance in the class distribution. So even if the class distribution is highly imbalanced, this will tell you how good or bad this model is. And since all the dots on this line, what is the threshold used to create that dot, you can look at this line and based on what is the right amount of true positive rate or false positive rate you want in your model, you can pick a threshold based on that. So if you want to minimize the amount of false positives, for example, if you are using this model to send out direct marketing campaigns or to identify who the tax department should audit, you can use a higher threshold. And in case you want to maximize the true positives, for example, in the case of fraud detection, or in the case when the radars are trying to detect if there's a presence of enemy fighter jet in the airspace, then you can use a lower threshold based on this analysis. I hope you found the explanation of all these concepts simple and easy to grasp. If you want to see more videos explaining other machine learning algorithms, just like I explained these ones, please let me know in the comments below. Thank you so much for watching. In this video, I'll give a very easy to understand and intuitive explanation of a very popular machine learning algorithm called k-means clustering. Now, clustering is a very useful machine learning algorithm which has a wide variety of use cases, and the best part is that it belongs from the class of unsupervised machine learning algorithms, which means you do not need training labels to create these machine learning models and get some benefit out of it. Now, to explain k-means clustering, let's try to look at some real life scenario. Let's say you work in a marketing department of a superstore and you want to introduce some personalization to the email campaigns or direct mail marketing campaigns, and you want to segment your customers into different categories so that you could create those emails much more personalized rather than just sending the same kind of emails to everyone. Now, of course, if it is a real life application, you'll be looking at a lot of factors, but to keep things simple, let's say you just are looking at two data points. One is that what is the age of the customer and how much they have spent in the last 1 year in your store. And of course, based on that, you'll have some tabular data which will give you the value of these two columns for each of the customer you have. Now, in order to give an intuitive explanation of it, let me draw some sample data point on a graph so that you can visually see what is happening there. So let's say on y-axis, I have the age, and then on x-axis, I have how much the customer has spent. So spend is on x-axis and then age is on y-axis. And let's say when you plot all these points on this graph, it looks something like this. So you have 2, 3 points here, and then you have 2, 3 points here, and then you have 2, 3 points here. Now, when you visually look at it, you can definitely see that there are 3 clusters here. But that is only possible because you are looking at 2-dimensional data, because you just have these 2 dimensions here. If you had more than 2 dimensions, even 3, you still might be able to visualize, but once you have 5, 10, 100 dimensions, and then there is no way that you could visually look at the data. So that is why machine learning algorithms like this come in handy, because the math what we see applies to 2 dimensions can also apply to 100 dimensions, even 1000 dimensions. Let me write down as I go along what are the steps we'll be performing for this model. So the first step is that we have to decide on the number of clusters. Now this is the biggest limitation of this model, because if we do not know what the underlying data distribution look like and we have no way of visualizing it when we are dealing with a lot of dimensions, how can we tell that what is the right number of clusters? So this is the biggest limitation of this model. We'll see shortly one trick we use to find out what is the right number of clusters, but let's say in this case that the number of clusters is 3, and which means that this value of k here is 3. So once we have decided on the number of clusters, the second step of this machine learning algorithm is that we initialize the centroids. And for that, we randomly pick 3 data points from this and initialize them as different clusters. So let's say since our k value is 3, we'll be picking 3 random data points from this and use them as our centroids for our 3 clusters. Let me use 3 different colors so that you could visually see what's going on here. Now let's sort of take a worst case scenario. Let's say we pick these 3 as the centroids for these 3 clusters. So this is my green centroid, this is my blue one, and this is my red cluster centroid. Now what we'll do is that for each of these data points, we'll measure their distance from each of these and then decide which cluster they should be assigned to. So even for this, we'll compare it against the distance from itself, and then this one, and then this one. And of course, for these 3, they are already at the centroids of their clusters. They'll stay like this. But for these data points, we'll measure their distance from this thing, and then this one, and then this one. And since blue is the nearest from these 4 data points, they will initially be assigned to this blue cluster. And when we look at all of these data points, and for each of these we'll measure the distance from this one, and then this one, and then this one. This one again might be assigned to blue, but this one, since it might be near the red one, it will be assigned to the red cluster. And this was our step number 3, which was assign clusters, which we just did. Now the 4th step in this process is that we have to move the centroid. Now what is the centroid? Centroid is the central point for each of the cluster. When we initialize the centroid, we just picked random 3 numbers and we initialize them there. But now it's time for them to move. How would we move it? For each of the clusters, let's take this blue cluster. So it has 1, 2, 3, 4, 5, 6, 7 points in it. What is the average value of age? And we'll get some point. Let's say we get 4.7. And then what is the average value of spend for these 7 customers? And let's say we get something which is $68. And so that would be the mean value of these 7 customers. And let's say that point is somewhere here. So this is our new centroid. Let me say centroid 1 for the blue dots. Let's do the same exercise for red. So red has 2 points. And when we take the average value of these, let's say we get somewhere here. This is the new centroid of red points. And let me say to 1, because this is the first time we are calculating the centroid. And for green points, since it is only 1 point, it will remain here anyway. So it will stay like this. Now this step number 3 and 4, we have to repeat them again and again till we see that there is no movement anymore of the centroids. Moving back to assign cluster step, now we have to again assign clusters. Now when we assign these clusters, they'll again be blue because their nearest point is this centroid of blue. So let me again, so these will again be blue. How about this one? Since now it has another candidate, it could be blue, which is here, or it could be red, which is here. I think the distribution will still stay the same because it is still near this blue point and this is still near this blue point. However, this will still remain red. But these points, since they are now near green, so their cluster assignment will change. They will become green because their distance from this, and this, when we compare it, it is near green. So they will become green. Okay, so we assign the clusters, we again move the centroids. These 6 points we have for the blue cluster. And since if there are more blue points here, this centroid will be pushed somewhere here, near them. So let's say this is the second assignment of the blue cluster. Now for red, there is only one point which has the red cluster assignment. And when we take the average of it, this itself will become red centroid. Since all of these three are green, so its centroid will be somewhere in between these. So it becomes its centroid. And the number I've written 1, 2, it's the second iteration of this. Cool. Now again, we have moved the centroid. Now let's go back to step 3 again and then assign the clusters again. Now let's see what happens now. When we look at blue ones and take its distance from this thing, and this thing, of course they're all near blue, so they will still stay blue. When we look at these ones, they are very near the centroid of the second one, so they will become red. And when we look at these, since they are again very near the green one, so they will still stay green. Now we again go back to this third step, which is we move the centroid. So the centroid for blue one, since these are the 4 points, it becomes like this. And for red one, it becomes in the middle of it. And for green one, it will still stay the same. And now the solution has converged. Now it doesn't matter how many times you move again, these centroids, they will not move again. That is how we know that we have converged, and hence that is the 5th point, which is we have finished when we converge. So this is a 5-step process which we have to take to identify that what are the k number of clusters present in the data. Since we just 2 features here, because it is visually easy to understand, it is applicable and can be expanded to as many dimensions as we want. Now coming back to the question of how do we know what is the right number of clusters when we cannot visualize the data, we use a very neat trick. It is called elbow method. Let me show what it means. So we do a plot like this, where on x-axis we have number of clusters, and on y-axis we track something which is called WCSS. It basically means within cluster sum of squares. The basic idea between WCSS is that, let's say if this is our cluster and this is our centroid, then for each of these data points we'll measure the distance from this, all of them, and this will give us some number. So let's say this is 3, this is 4, this is 2, this is 1, this is etc. So as the name applies, it is sum of squares. First we take square of all of these and then we sum them up, and that gives us a number. Let's say it says 68. Now that is the value of our WCSS. It indicates the total error present in this cluster. If all these data points were located on the centroid, then this WCSS would be 0. If they are very far away from the centroid, then this WCSS would be a very large number, which we are trying to capture here. So as on the x-axis we have number of clusters starting from 1 all the way to going to maximum clusters we can build. What we would see is that when we just have one cluster, which is going back to this example, let's say if all of this is under one cluster, we'll see that the centroid would be somewhere here, and then the distance from each of the cluster would be very high. So our WCSS would be a very large number, let's say somewhere like this. Now when we create 2 clusters, let's say if we were to take 2 clusters here, it will probably become something like this. They will go to the one class, and then this will go to the other class, and its centroid would be somewhere here, and its centroid would be somewhere here. We'll see that the error for this one would be small, but for this one will be bigger. So it will still be higher than 3 clusters, but still relatively less as compared to 1 cluster. So we'll see the error will go down. And for as we create 3 clusters, it again goes down, and then it will keep going down. It will never go up, because as you approach infinity here, let's say if you had 10 data points here and you create 10 number of clusters, then for each of the data point, that point in itself would be its centroid, and its distance from that would be 0. So as the number of clusters approaches number of data points, we see that the error, which is WCSS, it approaches 0. So we'll see that it will eventually approach 0. But in real life, when we look at this curve, we would see that it is not very smooth all the time. Sometimes we would see a curve which looks like this. Then we can see that there is a point where we saw a significant amount of drop in WCSS, and then afterwards there was not much. So that could be a good data point for us to take as the number of clusters, and in this case it could probably be 3. This is called the elbow of this curve, and based on this method of finding the right number of clusters is called elbow method. Now a quick recap of the steps here again. We start with the number of clusters. Initially we have no idea, hence we take as many number of possible clusters one after another to see what is the right elbow. The second step is that we initialize the centroids for any 3 data points we want. The third step is that based on the centroid, we calculate the distance of each data point from that centroid, and based on that we assign the clusters. The fourth step is that we move the centroid to the average value of all the data points within that cluster, and we'll keep doing this back and forth till the centroids do not move anymore. And once they do move, we know that the solution has converged. And then again we change the number of clusters and we redo all of this, and at every stage we keep calculating within clusters sum of squares to see that how the error is dropping as we are creating more and more clusters. And based on the elbow method, we find what is the right number of clusters to be used, and then we use that for the final model which we build in the production. In this video, I'll be giving a very easy to understand and intuitive explanation of some of the very popular tree-based models. We'll be looking at random forest, gradient boosting trees, and XGBoost, and I'll try to use minimal amount of math to give you an explanation which is very intuitive and easy to understand. This lecture builds on top of your knowledge for decision trees, which I have covered in the previous video. If you haven't watched it, you can watch it now. But just to make sure that everyone is on the same page, let me give a very brief refresher of how do decision trees work. Decision trees mimic the human decision-making logic. For example, if I have to make a decision of should I go outside to play tennis or not, it will depend on a bunch of factors. First, I have to decide, do I really want to go and play tennis or not? Second, if I want to go, what is the weather outside? Third, do I have a company with whom I can play tennis? And based on that, I keep making decisions, and the final output is whether I go for tennis or not. Decision trees are very powerful algorithms, but if you look in practice, most of the time, single decision trees are not used in practice. And the reason is that we do have advanced techniques where we combine a lot of decision trees to make the predictions, and these predictions are much more robust and much more powerful. And since we are aggregating the results of many decision trees here, these are called ensemble trees. So the first ensemble tree algorithm we'll be looking here is called random forest. The word forest here indicates that there are more than one trees, and what does random here mean? We'll come to it in a bit. When you look at all these ensemble tree models, they're all based on the principle of the wisdom of the crowds. And basically what this means is that the knowledge of the crowd, even if they are not very well educated, is much better than any individual, no matter how much learned they are. A very practical example of that is the show Who Wants to Be a Millionaire. You might have seen the Indian version of it, which was called Kaun Banega Crorepati. Now in that show, there was a helpline which was called Ask the Audience, in which the person who is giving the answers, whenever they get stuck, they can ask the audience around them on what they think is the right answer. Now the person who is actually playing in the show, the participant, he is usually much more learned. He has done a lot of preparation for the show, but the participants there might not be learned and definitely have not done any preparation. But usually what we see is that when we aggregate the results of all the audience, it usually converges to the right solution. So that is what this ensemble tree based models, including the random forest, tries to do. So as I said, there are more than one trees. So on the same data, let's say if I have this one data set. We'll train more than one decision trees, and at the time of prediction, we'll take the prediction from each of these, and in the case of regression, we'll just take the average of what all these trees say, and in the case of classification, we'll just pick the majority based on what all these trees say. Now there is one problem, and the problem is that if we use the same way of building the trees, then all these trees will be the same, and instead of relying on the wisdom of the crowds, it will just be relying on the wisdom of one and asking them the same question 1,000 times. It will be just like if in the Kaun Banega Crorepati, the person who is sitting on the hot seat asks the same person same question 1,000 times instead of asking the 1,000 participants that one question. So the solution to that is that instead of passing on this entire data set to each of these trees, every time we pick a random sample from this, for example, sometimes we pick this, sometimes we pick this different data set, sometimes we pick this different data set. So every time we randomly pick different subset of the data and then we pass it on to these decision trees. Another cool thing which we do is that if this data has, let's say, 5 features, then not only we are restricting the number of rows we are sending to each of these decision trees, we restrict the number of features which we send. So for example, we'll just send 3 features to this one, 3 features to this one, and so on and so forth. And all of these would be again randomly selected features. So some decision trees have to rely on the power of some of the features, which actually makes sure that we are extracting the maximum amount of prediction power out of all these features. And since we randomly select the rows and we randomly select the columns, that is why it is called random forest. One great thing about these random forests is that all these trees, they can be trained in parallel, which means that if you are using different cores or different machines, then you can parallelize this process of training all these decision trees and then at the end aggregate the results, which makes it a very popular choice for dealing with large amount of data because you can parallelly distribute the training of all these decision trees, which makes this algorithm perform much more faster. And that is why it is one of the go-to algorithm if you are training on very large amount of data set and you want to attain a good amount of performance from your model. The other ensemble model which we'll be looking at is that of gradient boosting trees. Now gradient boosting trees further enhances on what we learned during decision trees and random forest, and hence it is even more powerful algorithm. In my 10 years of experience as a data scientist, if I have to pick one model for any prediction task, gradient boosting is my go-to algorithm because it is incredibly intelligent, and most popular machine learning algorithms, for example scikit-learn, supports this model. Now this is a little bit complicated model. I'll try my best to explain it in the easiest possible terms. Most of the videos out there I saw, they were very math heavy, usually skipping on the intuition of it. So I'll try my best to keep the math low and just focus on what is the intuition behind training this model. Here again, we will be building a lot of models. Since this is also an ensemble tree based model, it has a lot of decision trees within it. But trees are not created in parallel, just as we saw in the random forest. Instead, the trees are created sequentially, one after another. So we'll say this is initial tree, and then we have another tree, and then this passes on to another tree. And each tree builds on top of what was the knowledge gathered in the previous stage. To be precise, every tree looks at what is the performance of the previous model, what are the errors of these model, and then tries to minimize this error when this is giving prediction. And same goes here. This model looks at what are the errors which are produced by this model and then tries to minimize that in its predictions. Let me explain it with a little bit concrete example. Let's say we have a house pricing data set where we are trying to predict what will be the house of the price depending on factors like number of bedrooms it has, what was the year it was built in, and what is the square footage this house has. Let me create some dummy rows for this data set. So we have bedrooms and we have price. Now for this data set, what we'll try to do at each of these model building stage is that we'll try to see what is the model prediction, what is the error in it, and then feed that error into the next model so that it can try to minimize this error. Now this model again will produce some prediction, and then there will be some error, and then we'll pass it on to the next model. And we'll keep doing this till we see that the error is approaching 0. So basically the fields which we'll be adding here is for this model 1, which is also decision tree. We'll see that what is its prediction, let's say prediction 1, and then what is the residual, which is basically error, what is residual 1, and then we'll be looking at what is the prediction 2, and then residual 2, and then prediction 3, and then we'll see that what is the residual of the third prediction. Now, since we do not have any model in the very beginning, so how do we create the predictions and how do we create the residuals? What this algorithm suggests is that for this prediction 1, which is our baseline prediction, we just take the mean value of all these points. Since the mean value of all these points is 477,000, we'll just fill this in here. So it is the same value for all these points, regardless of how many square foot they have, what is the number of bedroom they have, regardless of anything, it will be the 477,000 value for all of these predictions. Now, once we have calculated the prediction, the next step is to calculate the residual, which is basically the error between this price, which is the actual price, and then this predicted price. As we can see, the error here is about 168K, and let me fill in the rest. Cool. Since I filled these values, the next step is to calculate the prediction for this second model here. Now, one thing which we will do different here is that this is our X, which is the input variables which goes into the model. And usually price is what we are trying to predict. But in this case, since we are trying to build on top of the error value of the previous models, instead of passing on the price as the Y parameter, we'll pass in this residual error as the thing which we are trying to predict using this machine learning algorithm. So our Y would be this residual of the first machine learning model which we have built here. Now, while we are training this second model with this as the output variable, we'll try to do one thing, which is that we'll intentionally try to make these models not very strong and not very robust. And we'll intentionally try to make these following decision trees a little bit weak learner, because the theory of the wisdom of the crowds indicate that to get the best results out of the crowd should be weak learners instead of very strong learners. Now, the way we do this is that we minimize the depth of the model which we'll build. I've built the model on my machine. Let me show what it will look like. At this stage, since we are getting the results from the second model, let me call it model 2, where our baseline model M1 was just the average value of it. So this model will look something like this. So now we have the model trained. Once we pass it on into this and fill in this predictions too, it will look something like this. Now we know what is the prediction 2. We want to get the residual error of this second phase. And the way we do this is that we take what was the actual price, which is here, and then we minus this residual, and then we minus this residual here. So in this case, you can see it will be 615K minus 168 minus 477K plus this residual here, which is 147K. Now this usually leads to overfitting. So what is advised is that we multiply this number with the parameter which is called learning rate, and it is between 0 and 1. The best practice is that we use 0.1. So we'll multiply this with 0.1, and the answer which we'll get in this case would be 153K. Similarly, we'll take the second row. So it'll be this minus this and then plus this. So it'll be 526K minus 477K plus 0.1 and then this value, which is again 147K. And the output would be 63K. So let me fill out all of these here. Now we'll repeat the same process here for our third model. This will be our X. The features will remain the same, but instead of training on residual 1, this time we'll be training on residual 2, because this is what we want to pass on to the third model. I've trained this model on my machine and I've got the predictions out of it. Let me fill out what the predictions will look like. So now once we have calculated our prediction 3, again we have to calculate the residual error 3. And the way we calculate this here is that since we'll use this same equation here and we'll further add this 0.1, which is our learning rate, and then multiplying with this number here. And once we fill it out, it will look something like this. As you can see, now there is one thing which is worth looking here, which is when we look at the first residuals, it was 168. our second residual was 153, our third residual is even lesser than that. And as we keep progressing, we'll see that our errors will be going down. You can see it is the same scenario here, 69K, 63K, 58K. And gradually the errors are going down to zero. And the reason this is very gradual is that because of our learning rate. Now let me briefly explain how does learning rate work. So for example, this is our x-axis, and here we are taking number of models or number of iterations. And on the y-axis, we are seeing that it is our total error. Now, ideally, we know that the error should be zero. It should be somewhere here. So in the first time which we build the model, it is possible that the error is right here. Now, if your learning rate is very fast, your model will try to converge very fast towards this. So it will move here in the next iteration. And then the next iteration, instead of going here, it overshoots because the learning rate is pretty high. So it is possible that it again goes here. That is why it is recommended that you take small steps. It will take more time to converge, but the convergence would be near. Let's say if we were to take small learning rate, what would the output be? Let's say again we start here, the next step is here, the next step is here, the next step is here, and we keep going down, and then there is a chance that we meet this minimal amount, and then when we see it is increasing again, we stop here, and then we'll find this optimal point. That is if we have a small learning rate. If the learning rate is higher, as we have seen in this purple example, then our solution would be this, which is not optimal. It will still have some error. We covered a lot here, so let me give a brief recap again. So in gradient boosting trees, unlike random forest, we are not building decision trees parallelly. Instead, we are making them sequentially. So it will look like this. We have first model, M2, M3, and so on. And at every stage, we pass on the errors from the previous model to the new model so that the new model can learn on it and then improve on top of it. And the way we do this is that we take the same features, but every time we change our output, the Y which we are trying to predict, and it is usually the error which is coming from the previous model. For example, res1, res2, and res3 in this case. But since in the very beginning we do not have a model prediction, we do not have residuals, so we take the baseline prediction, which is the mean value. So we take the mean value, we calculate the error, then we try to predict this error with a weak learner which does not have very deep trees, and then we get the second predictions, and based on that we calculate second residuals, and so on and so forth. And gradually what we would see is that this error is going down to zero. So at the time of prediction, we chain the values from all these models, and the prediction of each of these is multiplied by the learning rate, which could be from between 0 and 1, and then we sum all of them up, and that will be our prediction for each of the new input we see. Now that was a lot to cover. Now let's very quickly look at another version of these ensemble trees, which is even more powerful than gradient boosting trees, and it actually was built on top of it, and that is called XGBoost. Now XGBoost is a relatively new model. It is one of the most powerful models which are out there. It was invented in 2014, and in 2016 it was so prevalently used in Kaggle, which is the main platform where people compete for data science competition, that out of the 29 winners, 16 were using XGBoost. And based on that, it got so much popularity that even till date, in most of the competitions, you will see that people are extensively using XGBoost. It is a very powerful model, and it is built on top of the problems which we had with gradient boosting trees. Now I won't go into much detail of it. It is a very excellent paper to read. I'll post the link for the paper in the description below. But at an intuitive level, the main limitation they had with gradient boosting trees, since it is not a parallel machine learning algorithm, it used to be very slow when we were dealing with very large amount of data. So the way XGBoost tried to make it fast, it tried to do it in 2-3 ways. First, that it added the GPU support so that the computation could be much more faster. Second thing which they did was that they changed the data structure used to store the data. So usually when you have the data, it is stored in the row format. So a chunk of rows would be stored somewhere else, and the chunk of rows would be stored somewhere else. What XGBoost recommended is that we store it in a columnar way, so that some columns are stored somewhere else and some columns are stored somewhere else. The reason this was very big improvement is that this led to parallel processing. Now, as I said, a big limitation in gradient boosting trees was that they are not parallel. The way they introduced parallel processing in XGBoost is that they realized that one of the bottleneck while creating these trees was that we have to figure out that what is the right threshold based on which every column should be split. So let's say we are looking at, this is number of bedrooms and this is square footage. Now every time the tree has to make a decision on what is the right square footage to make a split, whether it should consider less than that and more than that, it has to do that calculation on a lot of potential candidates for each single column. And this is a big bottleneck bottleneck when we are training any tree-based models. Now in XGBoost, they realize that the flow of the models, which is let's say M1 and then M2, this is going to be parallel nonetheless. But when we are building model 1 and then when we are building model 2, at every stage, we have to identify that for each of these columns, what is the right splitting point. And that process can be parallelized because one processor can look at this column, another processor can look at this column, and so on and so forth. And here I'm just showing 3 columns. Imagine if there are 200 columns, then the process can become 200x faster if we have enough parallel computational resources available and we make it all parallelly distributed. That's all I wanted to cover in this model. XGBoost, though it's used a lot in machine learning competitions, does not get used a lot in the practical data science scenarios. The main reason is that most of the popular machine learning libraries like scikit-learn, PySpark, they do not support XGBoost. So though it is good to know how this model works, how it builds on top of gradient boosting trees, in practicality I've seen this model not being used so much because it's not supported in these popular machine learning libraries. I have covered a lot in this video. I hope that my explanation was